Today's topic is set theory. A set is a collection of objects. These objects are also called members or elements. If an object is a member of a set A, it is shown by this symbol here. And if an object is not a member of the set of a set, it is shown by a cross symbol here. Set can be of anything. Set can be set of numbers like integers, rational numbers, real numbers. It can be set of alphabets and can be set of anything. The first question on the set theory is how to represent a set. Since it is a collection of elements, so how do we represent those collection of elements? So there are two methods of representing sets. First is roster form or tabular form, and second is set builder form. In roster or tabular form, all the elements of the sets are listed and the elements are separated by commas and enclosed within braces. For example, a set of square of natural numbers in roster form is written like the example shown here. The second method to represent sets is set builder form. In this, the elements of the set is represented by a relation or a property which all the elements of the set possesses. For example, the set of square of natural numbers which was shown in the previous slide is it is written in set builder form like this. It is a set of A having an element x where x is equal to n square and n belongs to natural number. You can also convert set represented in roster form to set builder form or from set builder form to roster form. For example, if we have an element, if we have a set A of element x which is represented by relationship x is equal to n square where n belongs to natural number and x is less than 20. So if we want to represent this set in set builder form, we can vary n from 1 to and so on and such that x remains below 20. So if we use this relation, we find that there are only 4 elements in this set and these are 1, 4, 9, 16. We can also convert set written in roster form to set builder form. For example, the set A shown here are having elements 5, 25, 125, 625 and so on. If we look closely, we find that these are elements of 5 to the power n, such as the first element is 5 to the power of 1, second element is 5 to the power 2, third element is 5 to the power 3 and so on. So in the set builder form, we can write A is a set of element x where x is equal to 5 to the power n and n ranges from 1, 2, 3 and so on. A set can be of any type. It can be an empty set, it can be a finite set, or it can be an infinite set. An empty set is a set in which there are no elements. This is possible if there are no elements which satisfies the relation defined in the set. For example, the set A shown here is a set of element x such that x is between 1 and 2 and x belongs to natural number. Clearly there is no element object satisfying this relation and therefore A is an empty set. In the second example also, B is a set of element x satisfying the relation x square plus 1 equal to 0 and x is a real number. So since there are no real numbers satisfying the relation x square plus 1 equal to 0, B is also a empty set. Sets can be finite and it can be infinite. If the number of elements inside a set is finite, it is a finite set. If the number of elements in a set is infinite, it can be infinite set. For example, set of roots of a polynomial. Since the roots of a polynomial are finite, it is a finite set. And if you want to find a set of square of natural numbers, since there are infinite number of natural numbers, this set is also infinite. The next definition is the definition of a subset. A subset is denoted by this symbol. Now consider two sets A and B. A is a subset of B if for every element in A it is also in B. So then A will be a subset of B. For example, if A is a set of natural number and B is a set of integers, since all natural numbers are also integers, A is a subset of B. In this example, B is called the superset of A, denoted as with this symbol. The next definition is definition of equivalence of sets. Two sets A and B are equal if and only if each element of A is also present in B and each element of B is also present in A. In other words, A is equal to B if A is a subset of B and B is a subset of A. For example, the set A here is having elements 1, 4, 9, 16, and set B is defined by relation x is equal to n square, where n is natural number and x is less than 20. So the elements of this set are also 1, 4, 9 and 16. Since all the elements are equal in both the sets, A is equal to B. Now subsets of real numbers. A real number has a subset of natural numbers, and it has a subset of integers, and it has a subset of rational numbers. Intervals can be written as a subset of real numbers. An open interval between A and B is written as set of elements x, where x is greater than A and less than B. A closed interval between A and B is written as set of elements x, where x is greater than or equal to A and less than or equal to B. This is an example of an interval which is open in A and closed in B. It is written as set of element x, where x is greater than A and less than or equal to B. This is another example of an interval which is closed in A and open in B. This is written as set of elements x, where x is greater than or equal to A and less than B. Also to be noted that intervals can be converted into sets and sets can be converted into intervals. For example, the set A shown here is having elements x such that x belongs to real numbers and x is greater than or equal to 2 and less than or equal to 8. So this is a closed interval and it can be written like this. The example 2 shown here, we wish to write this interval, this open interval in set builder form. So we can write it like this. B can be a set of elements x such that x belongs to R and it is between -1 and 4. As we have seen previously, a set has subsets. So a power set is a collection of all the subsets of a set. We will try to understand this further with examples. Suppose that we have a set A having elements 1 and 2. How many subsets of this set A is possible? An empty set is a subset of A, and a set having element 1 is a subset of A, and a set having element 2 is also a subset of A, and a set having both elements 1 and 2 is also a subset of A. The collection of all the subsets of A is called a power set, and this is shown here. Now the next question arises, how many elements are there in a power set? So the number of elements in a power set is equal to 2 to the power of the number of elements in the main set. Now after seeing the definition of a subset, we realize that all the sets can be represented as a subset of another set. So a universal set is a basic set which contains all the elements which are relevant to that particular context. The set containing all the objects or elements of which all other sets are subsets is called a universal set. For example, if we write a set of natural numbers, The universal set for that set can be a set of integers or it can be a set of real numbers. Now we have seen previously there are two ways to represent a set bundle form or a roster form. Sets can also be graphically represented, and these graphical representation of sets is called a Venn diagram. A Venn diagram is consists of a closed curves in which the elements of a sets are there. A universal set is usually represented as a rectangular set. To summarize what we have learned up till now, we have seen the definition of a set. A set is a collection of objects called elements. We have seen that sets can be represented in set builder form or roster form. We have seen the definitions of finite, infinite, or empty sets. We have seen that two sets can be compared for equivalence, and we have seen how to compare them. We have seen the definition of subsets and power sets, and we have seen that intervals of real numbers can be written as sets, and we have seen that sets can also be graphically represented using Venn diagrams. That's all for this current lecture.